Hello everyone, March 13th. Alright, finish this fast. Pivot. Find the pivot integer. Given a positive integer, find the pivot integer x such that the sum of all elements between 1 and x inclusively, 1 and x inclusively, equals the sum of all the elements between x and n inclusively. Pivot integer x such that the sum of all elements between 1 and x inclusively equals the sum of all elements between x and n inclusively. Return the pivot. If no such pivot exists, return -1. I suspect it might be a mathematical solution because from 1 to n, 1 to x, right? So it's 1 plus x times x divided by 2. So basically this is equal to x plus n times n minus x. I think it's plus 1 because it's inclusive, right? And then divide by 2. That's actually not true. Should be this one. Wait, hold on. So we wanted this to equal, yeah, we wanted this to equal this, right? And in this case, when n is equal to 8, I'm just put it in. So it's 1 plus 6 times 8 divided by 2. And this is 6. No. Times 6, my bad. And then 6 plus 8 times 8 minus 6 plus 1 divided by 2. What is this? It's a 21. What is this? This is 3 times 7. Yeah, that's 21. Yeah, so we just need to solve this equation, right? Solve this equation, which is just x squared plus x equal to n minus x times n plus x. I haven't done this for a while. Plus x plus n, right? Because we do this, which is this one, and plus, and this is n squared minus x squared plus x plus n, and plus x, so we get 2x squared equals n squared plus n. N is already given to you, so all we need to know is if this is a square, perfect square. And when n is 8, it's actually we can just say n plus 1 divided by 2. That's just 1 plus all the way, right? So if it's 8, that's 8 times 9, which is 36, so which is fine. 1, which is 1, that's fine. 4, which is give you 10, so which is not fine, right? So yeah, we can do this. Okay, so in Java, how do I check if a number is a perfect square? Well, how do we get Java, let's say, SQRT? Is there SQRT in Java? It better be. Math.sqrt. So you need to turn it into an integer, right? So floor. It can do floor. Or you do this, and then you say x is equal to math.ceiling, x equal to math.floor. Ooh. Math.floor. Wait a second, it's a double. We can do double Wait, hold on. It can do double equals double? Compare the square. Wait, so double can be compared. What is this rule? Compare double. Hey, hold a second. We can compare double with int. It will promote the int to a double before performing the comparison. Oh. And double can be compared. How would you compare double then? Implicit widening conversion, that when you compare a double with an int, the int is converted to a double, so that Java can then compare the values as two doubles. So what is math.floor then? Rounds express a double value down when it returns it. Oh, so it's still a double, right? So it's a double, so it's not an integer, so it's just a double equals double. Huh. I'm not sure if that is the best way, but that's the way I'm gonna roll with it. That's what I'm gonna roll with it. Alright, so we're gonna use math. Some math computation, math manipulation shows that if n times n plus 1 divided by 2 is a perfect square, then the answer is the square root of that value. Otherwise such answer does not exist, right? So we can say int tester equal to n times n plus 1 hold a second, divided by 2, right? We say double sqrt, double res equal to math.sqrt test, and then if when I return res equal to math.floor res, is that right? Then we return an integer res, otherwise return -1. Okay, so that will be our answer for this one. Straightforward, very, very straightforward. Okay, let's run through some example. Yeah, bunch of negative ones. I've done this before either. Did I use the same method? Yep, I did. So nothing special to see here, and now we're gonna move on. Man, I thought it was a new problem. I was happy it was a new problem. But that's okay. That is totally fine by me. Ugh. Totally fine by me. Alright, so we're done with this. Next, we're going to do... we should need to upload this problem. Alright, we're going to use this double... the 2 heap. Okay? So I'm going to try this with a 2 heap. Okay, so solution 2, solution 1. So this solution is inspired by this one. Right, it's inspired by this one. It sorts nums first, and then use a min heap and a max heap to ensure that we always compare the current number, with the one that has the max distance to it. And since the numbers are sorted, right? Since it's sorted, each time we encounter a number that is eligible, we must record its difference, because that must be the optimal, right? That must be the optimal. Yeah, if it's within, then it must be the optimal. Because even if later we find something even closer, it doesn't really matter, because later on the value become bigger, the distance become bigger. That must be the optimal. That must create the minimal, right, difference due to the sorted nature. All right. So for this, we need import heap queue, right? Definitely, and we're gonna go for this heap queue. So first need to sort it. Then I say sorted nums. Go to sorted for I, n, in enumerate nums, and we're gonna do ni. Right, we're gonna do ni. So that will be our sorted number. Okay, so from low to high, and then we say min heap. Right, okay, I should do it this way. Max heap. I don't know why I do it 3 times. Right, we have a min heap, we have max heap, and then we just starting from the first one, and we just start go, right? And each time we go, we need to put it into the heap for sure, right? We need to put it into, so for ni in sorted nums, nums also we also need a res equal to 10 to the 9 plus 7. Okay, for ni in this, okay, now what we need is to go through the min heap to find if there's anything good for it, right? I'm going to say while min heap and min heap 0, because it's the min heap, right? And we need to say the difference between the two, right? The difference between the two. So it's ABS, right? So ABS minus I is larger or equal to X. Then res shall equal to minimum res ABS n minus min minus heap q dot heap pop min heap 1, right? That'll be the difference between this, and then we'll keep doing that, and also while max heap and ABS minus max heap 0 0 minus I, if that's large equal to x, and res equal to main res abs, and minus heap q dot heap hop max heap 1. Okay, once we're done, we'll go with the both. We say main heap dot, no, probably heap q dot heap push main heap. Now we're gonna push in I and n. Okay, and then we're gonna do almost exactly the same thing, but we're gonna do max heap, and we're going to add a negative value. Right, we put it in. So once we're done, then we can return res need annotate type. Well, we might as well just do this. Or they probably ask for type for both, I guess. Yep, they need both, they need type for both. That's fine. There's a list of integer. This is the same. Okay, let's try this. See if this is correct. I mean, I have deleted all my test cases to use the given one. Okay, it looks all right. Take a look. What? Okay, that was pretty bad. That was pretty bad. Expected 0 because x is equal to 0. Huh. X is equal to 0. Did you not put 0 inside? What if x is equal to 0? Why this one doesn't work? Because I did not. Huh. X equal to 0, which means you can always do it yourself. But this one doesn't really handle with yourself, does it? Okay, I think I should put these two ahead. Put it in and then handle it. So push to heap first to handle the edge case where x can be 0. Yeah, but we might as well just, we can do a separate check, right? If x is equal to 0, then we definitely do it this way. Otherwise, you don't really, you know what? I'd rather do this. If x is equal to 0, then we just return 0. I think that's the edge case that does not warrant the performance degradation of doing this way. And I think this is O and log n. Right. Alright, let's try this one again. Yeah. Much slower, but it works. Kudos to that solution. Was pretty good. Right, very decent. Very, very decent. Okay, so this one is done. I've voted. Okay, move on. Apply operations to maximize score. You're given an array nums of n positive integers, n positive integers, and an integer k. Initially, you start with a score of 1, you have to maximize your score by applying the following operation at most k times. Choose any non-empty subarray that you haven't chosen previously. Oof. Choose an element x of the subarray with the highest prime score. If multiple such elements exist, choose the one with the smallest index. Multiply your score by x. Here, that denotes the subarray num starting in the index L and ending in R, both inclusive. Prime score of an integer x is equal to the number of distinct prime factors of x. Prime factors. Return the maximum possible score after applying at most k operations. Alright, so okay, your initial score is 1. You have to maximize your score by applying the following operation. Choose any non-empty subarray that you haven't chosen previously. Choose an element with the highest prime score. So I can produce the prime score. That's just added complexity, right? Prime score can be pre-computed, right? Now, with a pre-computed prime score, we know, given any subarray, which one to choose. Right? We know, given any subarray, which one to choose. That is actually not quite true. It's, if you want to really know, given any subarray, which one to choose. The prime score. So basically it's prime score and your index. And if we use a subarray, and I can do at most k times. What if L is equal to R? If we are equal to R, then I can just choose a specific, and just choose the largest prime score and multiply the score by this x. Yeah, like what stops you from just doing this? Why would you choose this? Right? I can just choose individual. All we need to do is first, like I say, we pre-compute the prime, like the prime score. So if I have number 8, 3, 9, 3, 8, okay, prime score is 1, 1, 1. Dude, help me. Everybody's 1. Right? Everybody's 1. So if we rank them, right? Rank them. Because whatever you choose, you have the highest prime score. Yeah, what if I just choose a single one? And then k, basically just choose 2. Right? Choose subarray nums 2 to 2. Numbers 2, 0, 1, 2 is the only element in the subarray, hence we multiplied the score by nums 2. Choose subarray 2 to 3. Oh, this is the trick. So when you choose it, as long as the same LR pair does not show up again, that counts. Holy crap. Ooh, okay. Now I see. Now I see. Huh. Oh, I cannot choose 19 again because this has a prime score higher than 19. So if I want to choose 19 to 12 or anything, 19 will not be chosen. So I pick 19 first, then I pick 18, right? But the next I can pick 14. So 19 times 18 times 14. Yeah, I can choose 2, 0, 1, 2, 3, but I cannot 2. So definitely, the base case is just you find the max value and you multiply them together. But if you do that, this one will become 9 times 8, right? Because this one has some special properties. So what you need to find is, so you find all the largest numbers, right? You find the largest numbers, and in fact, you find the largest numbers, and you start from the largest number and then going right. In fact, no, the largest number you also check, right? You find the largest number, and you also check its, you check its prime factors, right? The prime score, right? So you have the prime score of this, and I would say you start to look around to see how the prime score is distributed, right? Because we want to choose the max value as many times as possible, and the only way to do so is to start from the max score and then you go towards the right, or you go towards the left. Yeah, so you need to find what is the maximum range of numbers, right? Whose, okay, I'll be like this. You're starting from the max value, then you go left. Or you start from any value, right? The current value. Then you go left. And you check their prime scores, right? If you go left, you have to guarantee the prime score is smaller. So you keep going until you find the first one that is bigger than you. That's the same as you, right? So you have the amount on the left. So yeah, if I have a max here, right? I have a max here. Now I look to this with a smaller p score, prime score, and then we look this way for no larger prime score. So eventually we'll get a range. So within this range, as long as max is involved, no matter how you slice it, right? No matter how you slice it, max will always be chosen. So that can tell you how many times this max value can be chosen. So you do this for every single number. Every single spot you do it with a max number, right? You do it for, you just check, right? Once you finish, you get a range, and then you can compute how many different combinations you can get, right? So the combination will be ending at this max. So you have however many like possibilities. Starting with max, you have however many possibilities, and starting from beyond the max, and here beyond, so you have this multiplied by this, however many possibilities. But in fact, what we can just say, because you're starting from all these, so you find all of these, multiply by all of these, so you know have the total number. If that is larger than k, large equal to k, that was the answer already, just this one to the kth power. If it's not, then you have the remainder, and you basically say you cannot use this range, which you won't use this range, right? But hold a second, you might. What if we have a max and the second max right next to it? If you have the max and the second max right next to it, then after you finish computing the max, there's not that many ways you can use the second max, because they will all be inclusive, right? They will all be inclusive. Holy crap. Yeah. How would you handle that? if it depends, right? If the second max has higher, if second max is included in the range for the max, right? In the range of the max, if it's included, then it's will just be included. And when you handle the second max, you will go, left and right as well. But then when you hit max, you can now go, right? You can now further go. So, okay, so this won't be included. And yeah, so it won't include max, right? It won't include max because the requirement to include max is all the range will include this, right? All the range will include this. So if I have a second max is here, and if second max has higher prime score than the max, then the max will not include the second max. If second max doesn't have as high a prime score as max, or if it has equal, then as we go to the left, it won't include the max. So everything will be not including. So actually they're not, right? They're not overlapping. They're not overlapping. I think it's fine. They're not overlapping. So yeah, so we find max. We can just pinpoint every single one. We sort this thing, okay? And then from the largest value, we will sort based on value and then based on index, right? Based on index. We want the index to be, so we want the value to be big, but index to be small, right? Index to be small. And then we go for that. We go left and right, find its range. We get whatever we want. On the second one, go left and right because we have proven that even if they're adjacent, it won't affect. Okay, there will be no effect. Like if the second max is here, right? If the second max is here, and then when you go left, max will not include second max, but second max can include max, right? So it's fine, right? It's fine. It's just they will be different different ranges, subarrays. So we find them, we handle the max, we handle second max, just keep going, every single one, keep going, and it's guaranteed that I think each value will not run too many times, right? Because you don't go beyond. So all you do is within the current range, right? You don't go beyond. And well, from this you do go beyond though. You do go beyond. If it's bigger, right? Then it will, just go beyond. It will go beyond, and it will end at a certain point. So there is a risk of overflowing. So what I want to know is the max. Like if I go on the right, I want to know can a prefix max handle this? Because all I want to know is no, but if a prefix max, you only have max. But you can binary search, right? If it's prefix max on the prime score, and I want to know, right? Because I am at whatever I am at. Oh yeah, that's not gonna work. I need the prefix max starting from every single position. That is not happening. So that will require a segment tree, right? This requires a segment tree because I need to know, give me a range. What is the max value in this given range? Honestly, it's not a max value in this given range. What I want is like starting from this position, how far I can go, right? I have my current prime score and I have everybody else's prime score. I just want to know for my value, how far can I go to the right and how far can I go to the left? If there is a way to compute it fast, that will be very helpful. But except from just walking, right? You have to walk through this. I really don't know, honestly. Like, does there really exist a way to compute this? Yeah, even if you do segment tree, it's not gonna work because segment tree, all you can do in segment tree is to tell what's the min, what's the max, right? That you can do. But in the current case, you're not really telling the min and max. What you want is to know how far you can go. Which is essentially, yes, a prefix max on a score. But have to start at every position. You can't just do it once. You do it once, it does not work. Unless, yeah, there's no unless. Yeah, there's no way. Except for just loop through the whole thing. Then we have k, right? K has a certain value. And then you already spend some time, have to 10 to the 5th, so we can probably get all the prime numbers ahead of time. So that will be easy, right? You don't have to worry about that. We're gonna compute the score, that's fine. It's just given a range, right? Just given a range. How do we know how far I can extend? Yeah, I have the current score, I have the max value, I have the current score, and I have all the score around me. Basically, the question is asking how many on the left is smaller than me, like adjacent and smaller than me, and how many on the right, adjacent, is not larger than me. It's as simple a question as that, right? But for each one, you have to go out, you find the answer. And if the next one, you have to go out and find the answer again. Right? You have to find the answer again. Which is well, granted, when you find the second one, you won't like if it's on the right, you won't go beyond the first one. But you might revisit the same thing that the first one has visited. Yeah, that will cause it to time out, I fear. But we can definitely code it, right? We can code it even if it times out. We can code it. But I want to see if there is a better way, right? If there is a better way. Yeah, all I need to know is how far I can extend. That's it. How far I can extend. So yeah. So the question is, give me an array of values. Okay, and I have a value. Tell me how far I can extend. If I'm on the right hand side, how far I can extend such that every value is smaller than me. Yeah, that is the problem you need to solve. And hopefully using a log n time. Because on is a trivial case. Probably is not gonna work. Okay. Well, that'll be it. We'll keep this churning ahead.